Hi guys, just a quick lesson today about what's called sound intensity. Up to this point, we've really only talked about frequency and wavelength of waves. We talked about also the speed of sound. So the most recent lesson we had was about the Doppler effect, right? So we talked about how there's a shift in the perceived velocity of sound waves because of the Doppler effect. I'm going to scroll down because I kind of have my slides out of order. We talked about how when the source of sound is moving, it shrinks the waves down, so the perceived frequency is going to be different for somebody in front of the source, where somebody behind the source is going to kind of shift the frequency. But the other quality of sound that we can think about is kind of how loud it is. And this is sort of difficult to describe because there's actually a lot of factors that go into it. But what we call loudness really it's more easily described as sound intensity. So here I have a jackhammer as something you kind of think about as something with a very intense sound, loud enough that it could really hurt your ears. So what we can think about in terms of the properties of the wave is amplitude. So amplitude we know is somehow related to loudness, and we also call loudness volume. But these are all kind of somewhat different terms. The amplitude of the wave has to do with, remember that sound waves have to do with pressure. So remember that the pressure is really going up and down. We call these regions of high pressure compression, where all the air molecules are close together, and where there's a low pressure, we call that rarefaction, where the air molecules are more spread apart. So if something is a really intense sound or a really loud sound, what's really happening is there's a greater difference between the high and low pressure. So there's a more extreme. And this is really difficult to measure because we can measure kind of the power or we can sort of take a measurement of pressure, but it's really difficult on a small scale to measure these pressure differences. We know that they exist, but it's a little bit challenging to actually get a measurement of pressure amplitude. So what we really describe loudness with is a measurement called intensity. So if you think about the source of sound as just a single point, we could talk about just a single point in the center of a sound wave, and the sound wave is spreading out in all directions like a sphere. Okay, so it's spreading out and it gets larger and larger and larger, and as the sound wave gets larger and larger and larger, that same amount of energy is spread out over a larger and larger area.
Daddy, can I point to one of the balls?
You can point to one of these balls, so Ivy's going to come point to one. Okay. She pointed to all of them. Thank you, honey. That was a big help. Okay, can Daddy finish this lesson real quick?
Okay,
can you just sit real quiet here for a second? Okay, so the surface area of the sphere has to get larger and larger and larger as the sound spreads out. So we talked about this idea of like the wave size of the ripples on a pond. So a question then is, what would be the energy received at any one of these points? So this really depends on what is the surface area of a sphere. So surface area of a sphere, we can remember from you probably learned this, is the same thing as the derivative of volume if you're in calculus. So the surface area of a sphere is 4 pi times the radius of the sphere squared. So if we're thinking about the center of a single source to the edge of where you're actually listening to this, you can keep watching your movie, honey. The center of the sphere is the source, and then where you're actually hearing it, where the sound is reaching, would be like the edge of the sphere. So we could use the radius as the distance from the source to the edge. Yeah, honey, go ahead. Okay, so the radius gets larger, but then the sound is spread out over a larger area, so the surface area is larger, so it's probably getting less intense. So the way that we can describe sound intensity has to do with the power, how much energy is put out per second, divided by the surface area of the sphere. So our equation for intensity then is, so let me move this up so you can see it a little better. So the intensity of the sound is power of the sound, so that's like watts, right? Divided by the surface area of the sphere, which is related to the distance of the source. So 4 pi, which is just a constant, it's about almost 13. Also divided by the distance of the source squared, so that's like the radius squared. Okay, so this makes sense that the farther you are away from the sound, the source of a sound, the less powerful or the less intense it would seem. So let's work an example of this here. So question is, so we've got a trumpet here. What is the intensity of the sound waves produced by a trumpet at a distance of 3.4 or 3.2 meters when the power output is 0.2 watts? Assume that the sound waves are spherical. So we're looking for intensity here, so we don't have to rearrange the equation. So it would be I equals power divided by 4 pi r squared. So the power is 0.2 divided by 4 pi, and then I have to square this distance. Okay, so if I plug all that into a calculator, I'm going to come up with 0.00155. What would be the units here? So we have the power is in watts, and this is an area, so it should be watts per square meter. And those would be the kilogram meter seconds units, because these are all meter. Watts, remember, are the standard kilogram meter second unit. So watts per square meter is the unit for intensity. And is that loud? Like, what does this number represent? Well, lots of times when we're doing intensity, it's good to write in scientific notation. And actually, since I only have 2 sig figs here, I'm going to write this as 1.6 times 10 to the minus 3 watts per square meter. Okay, and so this would be 1.5 times 10 to the minus 3. So we have this thing that shows like what's our range of human hearing, what's considered really loud. So the lowest that you can possibly hear is like 10 to the minus 12 watts per square meter. But the threshold, or the region where we're normally talking and listening to music, is more up here. So this would kind of be a loud musical sound. So in the next lesson, we'll talk about relative intensity, which is when we're using decibels. Relative intensity has to do with, I'll do this problem in a second. Relative intensity has to do with, it's like a dimensionless unit where you're just comparing how loud something is compared to how loud you can actually hear. So this is a good way of describing if something is actually perceived to be loud by a human ear, whereas watts per square meter is just a unit of power over area, and doesn't give you a really good idea of how intense something is. So in the next lesson, we'll talk about relative intensity. I can do this last example problem here, or at least help you set it up. At what distance must a 40-watt speaker be if the intensity is perceived to be 2.5 times 10 to the negative 5th watts per square meter? So for this one, you'd have to rearrange it. So our equation is I equals P over 4 pi r squared. So if I'm looking for distance here, distance is r. Okay, so I'd have to rearrange this whole equation to solve for r. So I would multiply both sides by r squared, divide both sides by I, and take the square root. So r should be P over 4 pi I, and I'd have to take the square root of that. Okay, so in this case, it would be 40 divided by 4 pi, and then this 2.5 times 10 to the negative 4 times 10 to the negative fifth. Okay, and I'd have to take the square root of all that. And I lost the number on my phone because my daughter picked up a phone. So let me retype this in here. So 40 divided by and then I need to take the square root of that. So I come up with 356 meters. So 40 watts would be a really powerful speaker if you're hearing it that quiet, so it'd have to be very distant. So 356 makes sense. So what I'm going to do is I'm going to post a worksheet where you're just working out these power, intensity, distance problems. And this is going to be short. And in the next lesson, we're going to talk about how we can do decibel calculations, which are a little bit more complex because you need to use logarithms. So I'll post that hopefully by the end of the week. And that will be the last lesson before your spring break.